Hello, in this section, we are going to study the coalescence growth of particles. So we start considering the force-free case. So this means no force is acting between the particles. First of all, we start considering the collision of two circles in the planes. When the minimum distance between the centers of the two circles, d is larger than the sum of the two radii of two circles, r sub 1 plus r sub 2. Then we don't expect any collision happening between the two circles. But if the minimum distance of the d is less than the sum of the two radii of the r sub 1 and r sub 2, we expect the collisions between the two circles. In this case, we consider only the circle on the planes. But in a real situation, we consider the three-dimensional collisions. Then instead of the distance between the centers of the two circles, we need to consider the areas. We call such an area is a cross-section. We consider the spheres with the radius of the r sub 1 and the radius of the r sub 2 approaching together. When the distance between the two centers of the two spheres d is less than the sum of the radii of two spheres of r sub 1, r sub 2, then we expect the collisions of two spheres. So for example, if the center of the blue is in this position, we expect the collisions between the two spheres in futures. These areas we call the cross-section. Cross-section for collisions can be calculated. Pi times r sub 1 plus r sub 2 squares. We call that this is a cross-section for collision. Especially in this case, we don't consider any force acting between the two particles. So we call that this cross-section for collision is a geometrical cross-section. So this cross-section is independent of the relative velocity between the two particles. So we consider some practice. Calculate the mean free path of gas molecules in atmosphere of the Earth. The density of atmosphere is 1.29 gram per cubic meters. The mean molecular weight and the diameter of the molecule are given by 28.8 gram per mole and 3.7 times 10 to minus 10 meters. So at first we need to calculate the number density of the gas molecules. So number density can be calculated 1.29 kilogram per cubic meters divided by the mean molecular weight 28.8. We need to convert gram to the kilograms. 10 to minus 3 kilogram per mole. Then 1 mole is 6.02 times 10 to 23 particles. Then we could calculate. Then kilogram is going to be cancelled. Mole is going to be cancelled. So unit becomes 1 over cubic meters. 2.70 times 10 to 25 gas molecules per cubic meters. So we could calculate number densities. The size of the particle, diameters of the particle is given by d equals 3.7 times 10 to minus 10 meters. So we can calculate cross-section for collisions pi d squares. We just only consider the identical gas molecules with the same diameters of the 3.7 times 10 to minus 10 meters. Then it becomes 43 times 10 to minus 20 square meters. So mean free path can be calculated 1 over n sigma c. So if you consider the cylinders, then the area of the cylinder is a sigma sub c and the L. Then volume of these cylinders can be calculated. So sigma sub c times L. If you could find the single particles inside of these cylinders, we expect single collision happen between the gas molecules. We need to multiply the number density with the volume to find the number of the gas molecule in the cylinders. When the n sigma sub Cl equal to the 1, we expect a single collision happening between the gas molecules. So from this equation, you can find that L equal 1 over n sigma sub c. So you can substitute number density of n, a cross-section for collision of the sigma sub c. Then it becomes 86 nanometers. This is a mean free path for the gas molecules in the atmospheres. Then using this mean free path, you can find the mean collision times. Mean collision time can be calculated L over V. V is the velocity of gas molecules. It is equal to the sound velocities. So you can substitute 8.6 times 10 to minus 8 meters. This is 86 nanometers divided by speed of the gas molecule, about 500 meters per second. Then it becomes 1.7 times 10 to minus 10 seconds. So it's a very short time scale for a gas molecule to collide with another gas molecule in the atmosphere. Then now we'd like to consider the growth process of particles in a disk. Growth equation of particles can be expressed dm over dt equal to p sub s is the sticking probabilities times rho sub d times sigma sub c times u. So we could consider this big one is moving. Then this area is a collision for cross section. Sigma sub c unit times this particle moving with a distance of the u. So the volume can be calculated. Sigma sub c times u. So if you multiply the volume densities, you can find the total mass inside of the cylinders. Then sigma sub t can be expressed pi times capital R squares. For the u, the relative velocity between the particles can be calculated with the radial velocity of the WR. So as I explained, radial velocity of the intermediate particle becomes maximum. We could find out the relative velocity between the large particle and the small particles. And also the falling speed of the particle is dependent on the size of the particles. So relative velocity can be approximated by the difference of the falling speed of the particle toward the midplane of a disk. So we could approximate the growth equation of the particle. And the WR and WG, we have already discovered expressions. Growth equation of the particle can be expressed with this equation. Large particles sink toward the midplane of a disk or migrate toward the stars faster than the small particles. Difference of the speed can be approximated by the speed of the larger particles. A large particle collides with the small particles and captures them during the motions, leading to the growth of the large particle. If the small particles always captured by the large particles, we expect the p sub s is nearly equal to the 1. So depending on the collisional process of the particles, we need to use a different value of the p sub s. So we use p sub s as a parameters. Then we start considering the growth of small particles. Stokes numbers is equal to the 4.3 times 10 to minus 7. When the R sub b is 1 micrometers. So this number is much smaller than 1. Growth equations can be expressed this ones because this sigma sub d over 2hd is equal to the rho sub d. And the pi r square times st v sub k maximum value of the eta z over r. So we consider the small particles. This is the midplanes particle. Small particle is try to sink to the midplanes. So we consider the situation of the g is much larger than the eta r. So we remove this part, etas. Then v sub k is r omega sub k. And then we could write the equation of the sigma sub d 2hd times pi r squares st times omega sub k g. So we use a sticking probability p sub s equal to the 1. If the g is the position of the solid particle is nearly equal to the scale height of the dust-rich layers h sub d's, we can actually cancel these factors. We could estimate the growth timescale of tau is m over dm over dt can be becomes 4 over 3 pi times rho sub b times r over sigma sub d st t sub k. Then we can substitute st. Then it becomes 0.17 times sigma sub g over sigma sub d times the t sub k. Then for the Hayashi model, sigma sub g, sigma sub d, 1700 over 7 at 1 AUs. Then we can substitute this into the here. Then we can calculate the growth timescale for the small particle is 41 years. So it's independent of the size of the particles. So even if you consider 1 micrometers or 10 centimeters, growth time scale is about 41 years. In this calculation, we assume the sticking probability P sub s equal to the 1. Then we consider the growth of the large particle. We are going to consider the growth process of the large particle and the intermediate particles. Stokes numbers is given by mu omega sub k over f sub d. For the intermediate size, f sub d is given by pi rho nu u radius of the solid particles. So you can substitute nu is equal to Cl. F sub d is calculated pi rho Cl u r sub p. This is a drag law for the intermediate size particles. For the large particles, f sub d can be calculated pi r sub p squares rho u squares. Then we could calculate the Stokes numbers, and then we could calculate growth rate of a solid particle in a disk. So this is the result for the intermediate size particle and the large particles. Intermediate particles, the size of the particle is between the 3 cm to the 20 cm. Then growth equations can be approximated with these equations. For the large particles, the relative velocity between the particle and the gas of the U is approximated 1 over 2 eta v sub k. And then we draw the next figures using these equations and compare the growth time scale of the particles with the migration time scale of particles in a disk. These figures show the growth time scale of particles when the sticking probability of the P sub s is equal to the 1s at the 1 AU and also at 10 AUs. Horizontal axis show the size of the solid particle R sub B's from the 1 micrometer to the 1000 kilometers. The vertical line is a time scale in the unit of years. Orange curves show the growth time scale, and the blue curves show the migration time scales. Growth time scale is shorter than the migration time scale at 1 AUs. It seems a particle grows by accreting small particles, but migration timescale represents the timescale for a particle to migrate all the way to a central star. And also we use the ideal assumption of the P sub s sticking probability becomes equal to the 1s. In that situation, growth timescale becomes shorter than the migration timescale. The particle might prevent from falling to the central stars. It is difficult to form a large particle at 10 AUs because 1 cm particles migrate toward the stars before increasing its mass. So we need to consider some mechanism to speed up the growth process of our particles, especially around the 10 AUs. So in this section, we consider the growth process of a solid particle in a disk. Okay, this is the end of this section.